So chapter 24, talking about electromagnetic waves. And let's start out with like a right-hand rule question. Let's say we have a wave moving downwards. And say the magnetic field is to the right. Question is, what direction is the electric field? I'll give you a second to think about this one. So yeah, electromagnetic waves are oscillating electric and magnetic fields. So again, if the magnetic, I said the magnetic field, say, points to the right, that's at one moment in time. Then what would the direction of the electric field be? We get that from the right-hand rule. So if you put your fingers in the direction of the electric field and curl in the direction of the magnetic field, your thumb points in the direction of the velocity. And so to start with, the electric, magnetic fields and velocity, they're all vectors, they're all perpendicular to each other. So velocity and magnetic field form a plane, that'd be the board. So the electric field has to be perpendicular to the board, either into the board or out of it. And so use the right-hand rule to figure out which one. So in this case, it would have to be into the board. So fingers into the board, curl in the direction of the magnetic field, thumb points down. So the electric field would be into the board. Okay. And again, this is just at one moment in time. A short time later, the magnetic field would be pointing in the opposite direction. So, say it moves down a little bit. And now the magnetic field is pointing this way. Now the electric field would be coming out of the board then. So if the magnetic field flips directions, the electric field would as well. And just to check, the electric field out of the board, curl in the direction of the magnetic field, thumb points down again. So the right-hand rule works regardless of the, regardless of time. It always maintains that electric field, curl your fingers in the direction of the magnetic field, thumb points in the direction of the, that the wave is moving. Okay, so again, very rapidly, typically for electromagnetic waves, the electric and magnetic fields are oscillating very rapidly. For visible light, the frequency is somewhere around 10 to the 14 hertz. So that's extremely rapid, far faster than you could ever see or anything like that. Now, the speed of light we can just write 3 times 10 to the 8th meters per second for most, pretty much every calculation that we do. It's actually like, an exact number, 299,792,458. So you have to go to like 4 or 5 decimal places to even get a number different than 3, like 2.99,792. Well, you'd have to go pretty far to, you need a lot of significant figures before this number would need to be modified at all. So for any calculation we can do here, we just say C is 3 times 10 to the 8th meters per second. Now, the electric and magnetic fields are related to each other in magnitude by the speed of light. So let's say the magnetic field is 42 milliteslas. Just as an example, 42 milliteslas. What is the electric field then? And we can just plug that in. We'd, again, the only complicated part is getting the units to work out. So the electric field would be the speed of light times the magnetic field, which is 42 milliteslas. Now, an electric field has units of newtons per coulomb or volts per meter. So we want to get at least one of those. They're the same thing. A newton per coulomb is equal to a volt per meter. So let's get one of those two, whichever comes first. So a newton times a second is a coulomb meter times a Tesla. And a coulomb times a volt is a newton times a meter. So going across, we have meters, Teslas, newtons, seconds, coulombs, and volts. Bottom, we have seconds, coulomb, meters, Tesla, newtons, and meters. So everything cancels out. We have the electric field in volts per meter. So let's see, 3 times 42, that's 126. And then 10 to the 8 over 10 to the 3rd. So this would be 1.3 times 10 to the 7 volts per meter. And so really all the information contained in a wave, if you know what direction the wave is moving, you really only need the magnetic field or the electric field to describe the wave. Like here, we just have the magnetic field. We're given that, the direction and the magnitude, and using the right-hand rule and this relation, we can get the electric field as well. And again, these values are constantly changing. So but they're always related by this. So like the electric field, for example, could be described as a function of time. By a sine function, and magnetic field, same thing. And when usually we talk about either peak values or RMS values for electric and magnetic fields. All right, now one of the important things waves do is carry energy. And we can define the intensity, let's talk about the energy density of a wave. Probably the easiest way to write that is epsilon naught E squared. In general, we have both electric and magnetic fields. So let's write out the energy density. So we have 1/2 epsilon naught E squared. We know that's the energy density in electric fields, and magnetic fields store energy. That's the energy density for a magnetic field, but they share the energy equally between electric and magnetic fields. So we can get rid of that factor 1/2. We can say that this term is equal to 1/2 epsilon naught E squared. So overall, we get that result. Or we could say that this term is equal to 1/2 mu naught B squared. So we could also write it this way. So we can write the energy density in terms of the electric field or the magnetic field. And we define the intensity of a wave. We use the letter S for that. That'd be a speed of light times the energy density. So we can relate that to the electric and magnetic fields as well. So this would be like watts per meter squared. So this is what you'd be interested in if you were like setting up a solar panel and get the intensity of the light. And then I want to move on to polarization. So just write down the formula there. We have two formulas for polarization. So the intensity of the light, when it goes through a polarizing sheet, we draw this. So the polarizer only lets electric fields pass through in a particular direction. So if you look at it, just say a random ray of light, the electric field can point in any direction. So let's say that it happens to hit the sheet in this orientation, where the polarizer is only going to let light go through in, along this line. So like in practice, there's a lot of different ways they can build these polarizing materials, but they use these like long chains of molecules. They can like stretch them out, and basically it allows the electrons can move around on these molecules, but only along the molecule, not perpendicular to it. And so like electric field in one direction gets absorbed while the perpendicular electric fields can pass through. But it's only going to let things go through in this direction. And so we say that angle is theta. And so the component that actually passes through, it's going to be reduced in magnitude. This would be E cosine theta. That's the component that actually passes through. Now, the intensity of a wave depends on the amplitude squared. That's a very general result for waves. And that's why we have a cosine squared here. So that's how the law of Malus, M-A-L-U-S, he's the guy that discovered it. It's kind of a trivial result based on what we're doing, but Malus did this experimentally in the 1600s when they had no idea what an electromagnetic wave even was. So it was actually a big deal at the time. And but again, this is just like one particular wave that's passing through the sheet. If you look at most light sources, the waves have completely random orientations. And so if you have a lot of waves passing through, like each one is going to be affected differently because they have different orientations, but the net result is that the intensity will be reduced just by a factor of 2. So kind of explain why in the recording, but yeah, that's the result. So if you have completely random light hitting a polarizing sheet, the intensity is reduced by a factor of 2. So if you have like 100 watts per meter squared of unpolarized light, then it hits a polarizer, what gets through is just half, 50 watts per meter squared in this case. However, once it passes through the polarizing sheet, the light is now polarized. So what that means is that the polarizing sheet only lets electric fields go through in this direction. So now every wave that passes through is oriented the same way, in the direction of that polarizing sheet. So now here we had unpolarized light. And once it passes through, it's now polarized light. So if we put another sheet here, then if we want to find the intensity that gets through, that would depend on the angle. So now like the electric field's in this direction, this sheet would probably be in a different orientation. So we'd have to find the angle between the electric field and that direction of the next polarizing sheet. And then we could apply this formula. And then the very last topic is the Doppler effect. Where the frequency of a wave is affected by motion. So, if something is moving towards you, for example, the frequency that you observe would be higher than the frequency it's actually putting out. If it's moving away from you, frequency that you observe would be less than that. And you just have to remember that. Don't worry about the plus or minus, like there's a convention. Use plus in this case, use minus in that case. But just think about like you're counting wavefronts. So if you're getting closer to the source, you'll count more wavefronts in a certain time period than if you were standing still. Or if you're moving away, you would count fewer. So frequency increases if the objects are moving close together, decrease if we're moving farther away. And again, this really only applies to low speed compared to the speed of light. So generally it applies to anything we'll do in this class. And again, the Doppler effect can be a lot more complicated than this, but we're just looking at a simple case, like moving towards or away from, or there's relative motion, but along a line, and speed less than the speed of light, or not really that close to the speed of light. Okay, so these are the topics for chapter 24, and let's do a few problems and then we'll call it a day. So in chapter 24. Here's a very, very simple problem, but during a flare-up from a sunspot, X-rays are emitted. The distance between the Earth and the sun is 1.5 times 10 to the 11th meters. The question is, how long does it take for the X-rays to reach Earth? This is actually a very relevant question, like these solar flares sending radiation towards Earth. NASA did this very shocking study not that long ago, like a few years ago, where they found that solar flares, like a direct hit from a powerful solar flare, like a worst case scenario type thing, could practically destroy our civilization. And they calculated the odds of that happening in the next 40 years, and it was like 1 in 8. It's not that unusual for things like this to happen. And it's shocking because you think we've been around for a while. Why haven't we ever noticed this? And these kind of events do happen. They have happened in our past, and just nobody cared because we did not have an electrical grid. That's a problem. These solar flares could completely wipe out our electrical grid if they hit us just right and they're strong enough. And in the late 1800s, that actually happened. And they say if something like that happened now, we could be without electricity for possibly, months to possibly even years. So, like all our computers could be fried, and kind of amazing. Something that dangerous can happen so frequently, and it's just never been a problem until now. Hopefully, they're doing things to protect us from that. But anyways, this is a very simple problem, though. Like, how long will it take these X-rays to reach Earth and destroy our civilization? So, Sun, Earth. So they're moving at the speed of light. So this is a very simple distance is speed times time. So we just solve for time. So we have 1.5 times 10 to the 11th meters divided by 3 times 10 to the 8th meters per second. So the meters cancel out. We get our time in seconds. Let's do this. Let's say 15 over 3. So I wrote this as 15 times 10 to the 10. So so 10 to the 10 over 10 to the 8 is just 100. So 500 seconds. So that's how long it would take for that solar flare to reach Earth. Okay, so these X-rays from the solar flare would reach Earth in about 500 seconds. That's about 8 minutes. 8 times 60 is 480 seconds. So around 8 minutes. And again, we wouldn't know that this happened until the X-rays hit us. We couldn't see the solar flare because the light would travel at the same speed as the X-rays. All right, so that was a very simple problem. Let's do something a little more interesting. All right, still another simple one, but this is an equation I forgot to write down. Very important equation. In general, the speed of a wave is the frequency times its wavelength. For waves in a vacuum, speed of the wave is the speed of light. So let's just do this real quick question. Obtain the wavelength in vacuum for blue light, whose frequency is 6.34. Times 10 to the 14 hertz. So if we want the wavelength, that'd be a speed of light over the frequency. So we have 3 times 10 to the 8th meters per second. And then the frequency is 6.34 times 10 to the 14th. A hertz is a cycle per second. So I'll just do that. And I want to convert to nanometers. Because visible light best measured in nanometers. So the meters cancel out. So what we're going to have is 3 times 10 to the 17th power nanometers over 6.34 times 10 to the 14th. So I'm going to write this as 30 divided by 6.34 times 100 nanometers. So to get 30, it took 10 from here. So 30 times 10 to the 16, 10 to the 16 over 10 to the 14 is 100. This is going to be like 400 and some nanometers. 30 over 6.34. Yeah, so we got 473 nanometers. and that would be blue light. Blue light, that's visible light, is typically from 400 to 700 nanometers, somewhere around there. The lower end of the wavelength, that's what our eyes interpret as blue light. For the higher wavelength, we interpret as like red. So blue end, that's towards the lower end of what we can see. And again, it's kind of a fuzzy area to give a range because everyone's eyes are different. So people have different cutoffs. And of course, we're talking about humans. Animals have different ranges entirely. They can see light we can't, like infrared or ultraviolet. At least some of them can. They're like bees and snakes can see things we can't. Just like dogs can hear higher frequencies than we can hear. But yeah, a very straightforward problem. You get something maybe intensity or energy related. Here's one. A future space station in orbit above the Earth is being powered by an electromagnetic beam from the Earth. So we're going to shoot it with a laser or something and give it power that way. The beam has a cross-section area of 135 meters squared. And transmits an average power of 1.2 times 10 to the fourth power watts. So what is the RMS value of the electric and magnetic fields? Okay, so one equation I didn't write down. Intensity is power over area. And yeah, we have to put a few things together here. But again, if we can find, say, the electric field, then we know the magnetic field, just multiply by the speed of light. So let's just focus on finding the electric field. So power is, we can find the intensity, the average intensity. That'd be the average power over the area. So this would be 1.2 times 10 to the fourth watts over 135 meters squared. So yeah, you take like 1,000 from here, so 1,200 times 10. So let's say 1,200 divided by 135. So this would be 8.9, or sorry, 89. So that part's 8.9, but then times 10. So we have the intensity of the wave. And from the intensity of the wave, we can get the energy density. And from the energy density, we can get the electric field. So we have to put several things together here. So let me write down this equation. So we have S equals the intensity is speed of light times the energy density. And the energy density would be epsilon naught E squared. We're just focusing on the electric field right now. Now, the average intensity would be the speed of light times epsilon naught times the RMS average electric field squared. So we can solve for the electric field That'd be the average intensity over C epsilon naught. I didn't write down epsilon naught today, but when do we do that? So 8.85 times 10 to the minus 12 Coulomb squared over Newton meters squared. So again, the hard part's going to be the units. We have 89 watts per meter squared. Speed of light is 3 times 10 to the 8th meters per second, and epsilon naught so again, we want an electric field. So we want either newtons per coulomb or volts per meter. So we're going to throw several conversion factors on here. So first, a watt times a second is a joule. Watt is joule per second. Let's see what we can. Actually, this might happen fairly quickly. I'm going to try this and then we'll. Yeah, I'm trying to think what conversion factor will work here. Maybe we should just see what we have right now. Let's see what we have right now. Actually, I'll do one more. A joule is a newton times a meter. Now let's see if this does the trick for us. So I'll just write it up here. We have watts times seconds, Newton, meters squared, joules, newtons, and meters. On the bottom, we have meters squared, meters, Coulomb squared, watts, seconds, and joules. Oh, that one does not cross off. So yeah, what we get is Newton squared over Coulomb squared. So that's what we needed because we're going to take the square root. So we'll get the RMS electric field in newtons per coulomb. So now the number part, we have 89 times 10 to the 12th. I was going to do 8.85 times 3. That's 26.6. So let's see, just to make sure we got everything, 89 times 10 to the 12. On bottom, we have 26.6 times 10 to the 8th. So this would be about 3.3 times 10 to the 4th Newton squared per Coulomb squared. So now we just take the square root of that. So I'm getting about 183 newtons per coulomb. For the electric field. And if we want to do the magnetic field, magnetic field will be easy because just the electric field divided by speed of light. And again, that applies for peak values or RMS values. So why don't we just do this real quickly? We have 183 newtons per coulomb. Speed of light, 3 times 10 to the 8th meters per second. And we want to get Tesla. Tesla's out of this. So we throw a net conversion factor, a Coulomb meter Tesla, say Newton times a second. And now let's just cross off. This might actually work. So you're getting 183 divided by that 10 to the 8 on bottom. So 183 divided by 3 is 61. Let's see. We can write this as 610 nanoteslas. Okay. So any questions on that problem? That required putting a couple of different things together. Like we had to use these three equations. Intensity is the speed of light times the energy density. And also just the definition of intensity as power over area. All right, we have time for one more question. We should probably do a polarization. Or does anyone care, polarization or Doppler effect? Let's do a polarization problem. You just kind of grab a random one here. Oh, this one's a little interesting. Kind of relates to what we just did. So let me read the problem. I'll have to find it again. Okay. So a beam of polarized light with an average intensity so we have already polarized light, goes through a polarizer, and the transmission axis makes an angle of 25 degrees with respect to the electric field. Determine the RMS value of the light that's coming out the other side of the polarizer. So here we have S naught, hit a polarizing sheet. Let's call that S1, where we have a 25-degree angle. So let's say this was the incident electric field. This is the transmission axis. That angle is 25 degrees. So we have to do two things. First, we have to find the intensity of the light on the other side of the polarizer. And then like we did before, we'll use that to get the RMS value of the electric field. But I'm going to erase that picture just so we have room. Let's find S1. That'd be the incident intensity times the cosine squared of the angle. So 15 watts per meter squared. And the so you do cosine of 25.